Assalamualaikum warahmatullahi wabarakatuh, and good day to all of you. So I'm the next speaker in this workshop. I am Associate Professor Dr. Shamsia Mashoho. I am from the Department of Computer and Communication Systems, Faculty of Engineering, UPM. So my talk today will be on artificial intelligence in neuroimaging. So I am focusedly will explain on the basic principles on machine learning. So I think and I believe that many of you have heard about AI and ML. So I would like to emphasize on the differences between AI, machine learning or ML, or another term that probably familiar among all of you, which is deep learning, or we call it DL. So AI is the base class or the basic concept of all intelligence, machine intelligence. So it is a generic and covers any ability of a computer or a robot controlled by a computer to do tasks that are usually done by humans. So it can be a rule based, it can be a hard coded version, or it can be a more intelligence like machine learning or deep learning that they learn from the data set, that they learn from the history or experiences. So machine learning is the subset of AI where basically it requires feature extraction steps as input. So it is learning, okay, but you need to give important features or significant information in order for the ML to learn about the problem and try to find the solution. For DL, deep learning, the learning process is based on the raw data. So in neuroimaging, basically it is raw images that probably MRI, PET, okay, fMRI images that you don't have to do any pre-processing to the images. You just feed in your images and the deep learning can learn from those images. So it has many hidden layers to extract the pattern. So it is important for you to know that uh, deep learning has the feature extraction actually embed inside the deep learning model. So what it tries to do, that's why it has many layers, because it's the model tries to extract the information, extract the shape, extract the texture from the images itself. So it may analyze the diagonal, the horizontal, or vertical um, edges of the images in order to understand the pattern. So there are many broad areas of machine learning. Okay, so there are many methods, AI methods covered under these areas. So for example, you have the regression, okay, and then SVM, support vector machine, whereby you have probably you would like to classify between two classes, which is the blue group and the red group. And then you also have the k-means for clustering broad areas, whereby you don't understand or you are not sure about how many groups that this data belong to. So with the clustering, you can group them together based on the characteristics or based on the features that you fit into k-means. Next is decision tree. It is mainly used for classification and regression. So I think you are kind of familiar with it. However, the challenge here is you have to decide the threshold in order for you to um, to go down or to move forward inside the tree branches. For ANN, or artificial neural network, which is actually a classification area, it is actually consists of nodes and links. So here is what we call as hidden layer. So in ML, probably the hidden layer here is much simpler than deep learning, because we already pre-process the images or pre-process the data. So what we fit in here are the raw features or the identified features. Here is the hidden layer here is try to find the relationship between the features and your target output. So the this right side is the output layer, whereby probably it only has two. For example, it's normal or abnormal, or it can be three: normal, benign, or malignant classes. Yeah. There are many applications of ML in neuroimaging. So, in clinical applications, as you know, there are many research that have been done based on ML pertaining to radiology. It has many work have been proposed and studied, such as classification problem, risk assessment, segmentation tasks, early diagnosis, prognosis, and even prediction of therapy responses. So these are the main applications, main tasks that have been done using ML. The challenges to apply ML in clinical studies, basically because of lack of label data set. So for us and the engineers or the data scientists, we are very heavily rely on the label data set, because without the label or without the data set, there is no machine learning that can solve or find the solution for the problem. So many researchers propose a solution to this, because in order for you to collect and label so many data, meaning that you have to contact or you have to uh, acquire the data sets from many institutions, and then you need the radiologists to label the images one by one. So one of the solution is the crowdsourcing. Okay, so even Google today is already um, promoting on crowdsourcing initiative, whereby they are asking the public users to supply them with images, maybe a recording or whatever data that that is related to their study. However, in clinical studies, crowdsourcing may raise issues on validation. Okay, meaning that we are not sure who is the person or the respondent to the data set. So even though the data set has been labeled, but the um, the certification or experiences of that respondent, we need to confirm and recognize the expertise. So it, it's sounds easy, but kind of challenging. Second Second challenge is generating sufficient ground truth for a reliable validation of ML is time consuming. So this is what I have experienced based on my collaborations and project with um, um, Faculty of Medicine and working on the machine learning for radiology. So for many years, we have to rely on the doctors in order for us to know the ground truth, and for that they have to spend time to to do the segmentation or to label the images one by one. And we are not just talking about 10 or 20 images, but sometimes it's up to thousands of images. So, of course, the radiologists also have many other tasks to do. So, I think this is very challenging, because we need your expert to do the labeling. Next challenge is the limitation for effective interdisciplinary knowledge transfer in publication. So as you can see in many published papers, normally it is very discipline focused discussion. Okay, so for example, if you go to computer science or engineering journals, most of us are only explaining in detail about our algorithm without giving good information or good knowledge about the medical parts. So in order for the medical people to understand our papers, that's going to be very hard because they cannot appreciate about the algorithms because um, there is no connection to their area. Similar to us when we are reading the very focused medical focus papers. So we are, not familiar about the clinical studies whereby you are more focused on the population of the study, the sample size, and then you are discussing about the statistical findings of your analysis and etc. So looking at that, we don't have a good knowledge transfer between these two disciplines, and yet we are trying to collaborate and try to find solution for medical. Next is ML is still insufficiently intertwined with the clinical world, in part due to misalignment of target and methods. So this is for you and us to discuss about what is actually uh, the medical ones from the engineering, what kind of output that you want, what kind of um, computer aided computer aided system that you need in order for you in order for in order for us to help you in your clinical work. So in my slides later, I would like to highlight two uh, terms that probably not very familiar, or maybe the definitions are different. So for us, the features are the multivariate data that in aggregate are used to build and make predictions with a classifier. So features, we are talking about shape features, color features, structure features, texture features, or even in a 3D features, we have volume and etc. So those are the features. So we have all the mathematical calculation to represent the features, and it will be in numerical values normally. So for labels are for the data sets. So we can give labels in terms of binary numbers. It can be categorical. So for example, abnormal, benign, or malignant, or continuous characteristics of individuals that are used to train a classifier and are subsequently predicted. So this is a very focused name that you want to give to your data set. So previous work of ML in neuroimaging, so I only highlighted two here. So the first one is on the classification, whereby you can see this is the MRI atlas produced in order for us to distinguish between healthy patient and Alzheimer's. So as you can see that we are trying to highlight highlight the areas, the regions with the yellow and oranges color. Okay, so these are this is one way for us to highlight the region of interest for the radiologist to investigate further. In the second example is the young brains. Okay, so what we able to do is we segment the MRI T2 and T1 weighted images. Okay, and here, rather than we stick to the grayscale color, the normal MRI color, what we would like to do here is we segment the regions. Okay, where the fluid will be represented by the red, gray matter by the blue, and the white matter will be in yellow. So as you can see, the representation here is much easier for the radiologist to observe and detect the abnormalities. So there are 9 general steps in machine learning that I would like to highlight. Okay, first is to define the problem statement and decide the goal. So as you know that the main broad area are classification, prediction, and clustering. So firstly, we need to know what is the aim or the target of the work. Secondly, we will do the data collection. It can be primary data or secondary data. So primary data, you have to get all the ethical approval, and you have to deal with the patients. However, for secondary data, you have to ensure the data is anonymous. For third step, you need to do data preparation and feature extraction. So among the tasks that is included in this step is data cleaning if necessary, meaning that if you have many data, sometimes because different operators they are doing the scanning, so probably the quality or the region of interest is not inside this scan images. So therefore, this kind of data may mislead our machine learning model. So we need to remove it. Next is data labeling. So every image of every scanning, we need to label that. So if we are talking about segmentation, we need to do the segmentation of the region. If we only looking we if we are working on classification, meaning that we need to know what is the image is belong to which class. Then we choose the data representation. Okay. So it depends. If you are working with machine learning, you need to extract the features, okay, to represent the data well. Or if you are just using the deep learning, you just make sure that the image that you want to fit into the model is good quality. Um, then we divide the data into training and testing. So the normal rules is 70% for training and 30% for testing. Now, step number 4, you choose a model, a ML model. So as you know, there are many standard ML models that are now available in online. So it can be in Python, it can be in MATLAB, Scilab, or C++. So there are many variations. So normally, the ML models, if it's based on that one architecture, it it is similar, even though it is implemented in different languages. Step 5, you have to train the model using the training data set that you have selected in step 4. So, 70% of the data that you have cleaned, that you have labeled, you need to train it using the model. And then in step 6, you evaluate the ML model with the testing data. And the normal performance metrics are, so for classification, we are normally talking about accuracy, specificity, and sensitivity. For segmentation, we are talking about dice coefficient. We would like to know the differences between the segmented area by machine learning and segmented by the radiologist. And then for lesion identification, normally we measure in terms of precision and recall. In step 7, we do cross validation. Cross validation means we don't want to repeat the one cycle of testing and training only. So what we do, we will do this many times and we group them in batch. Okay, so this is to ensure that the model is not overfitting or not underfitting. Overfitting means it's uh, too customized to the data. So when you have a new data later on coming in, the model cannot classify or the model cannot predict the output. If it's underfitting, meaning that it cannot understand the trend at all. So even in the training, it already gives you many errors or low accuracy. So what we aiming for is maximizing the generalization. So model is good enough to predict or to classify data. It can be the data from the training and testing or even the new data that you fit in. In step 8, we are going, if we don't get the targeted results, we will do the parameter tuning. So parameter tuning is more or less to improve the model. What we can do is we can increase the epoch, meaning that the training duration of the machine learning. It may be the errors may be due to imbalanced data. So you need to collect the data and make it balanced. And then unreliable features. So probably the features that we extracted earlier is not contributing uh, or or not presenting the trends correctly. So we need to uh, um, analyze these features, and probably what we can do is feature reduction. Next, for deep learning, it's it really relies on the quality of images. So if the low quality of images is provided, therefore deep learning cannot extract the features in the model. So it may lead to many errors and failure to understand the trend of your images. So next step is just for you to repeat step 5 to until 8 until the expected results are obtained. So that's why it's a long process, because there are many modification are needed in order for us to achieve the best results. So as I highlighted before, patterns are important in machine learning, because machine learning will able to extract the features and produce target results if the patterns are exist, meaning that you can see the correlation, you can see the relationships between features and the output. If there is no features, no relationships or no correlation at all, uh, that's going to be very difficult. It will be a challenging task for machine learning to understand the pattern. So even though many people say that machine learning is just a black box, it's not. It's actually try to derive a mathematical equation in order to understand the relationship between the features, which is the input that you feed in, with the target output. So uh, if there is a relationship, then the equation can be created. So lastly, how to make sure the machine learning works? Firstly, from the medical side, disease characteristics must be identified well in order for us, the engineers or the computer scientists, able to understand or able to extract the features or characteristics that you have identified. Then good image quality. Again, especially for neuroimaging, or especially for radiology in general. So we need good quality images, because after all, we rely on the accuracy of the images. So if it is noisy, if it's blurred, so it's going to be very hard for us in order to develop good machine learning model. Next is large scale, varied, and clinically relevant annotated data sets are very crucial in order for machine learning to work. So the one of this step or solution is to have collaborative across multiple institutions. So this is to speed up the process and to ensure the credibility of the annotation. Lastly, we need to focus on the relevant outcomes. So basically, the engineering side, they would like to solve the problem, but sometimes the solution is not what the clinical experts want. So it's totally different thing. So in order to eliminate or to reduce that kind of incidents to happen, we need to work together and discuss on the relevant outcomes of the work. So all the target, the input should be clearly stated before the machine learning work started. So these are the references for my slides, and I would like to thank you for your attention. And if you have any concern or questions, you may contact me at shamsia@upm.edu.my. Thank you so much.